In this video, we're going to take a look at functions and function notation. But before we can talk about a function, we need to understand what a relation is. Mathematically, a relation is any set of ordered pairs that represent some relationship. And it doesn't necessarily have to be a mathematical relationship. For example, naming the child or children of parent X is actually a considered a relationship. For example, we could say Roy, comma Laura, because my father's name is Roy, but we could also have Roy, comma Lisa, because I have a sister. Actually, I have two sisters, so you could also have Roy, comma Rachel. So in this case, you would have a relationship between the parent, who's Roy, and then his three children. And so that's a relationship, and we could list those as ordered pairs. Even with, if you want a numeric example, think about the square of a number. We could think about the number -2, and its square is 4. The number -1, and its square is 1. The number 0, and its square is 0. So you can have mathematical relationships. You can have just in general relationships. And for every relationship, notice you have two values. You basically have an input value, which we normally represent with the letter X, and then you have a corresponding output value. When we want to look at those individual sets of inputs and outputs, that's referred to as the domain and the range. The domain is the set of all first components, or all of your inputs in the ordered pairs. And a lot of times, in notation wise, in math, we use the letter D to represent a domain. And the domain, again, is simply the first value or your input. It's the X value, the X variable, the input, or sometimes it's called the independent variable. Then you have your corresponding output, or the Y values. And if we look at all of those as a group, they're considered the range. So the range is the set of all Y values, or the outputs. And typically the symbol we see for range is the letter R. And so again, the range corresponds to your Y value, the Y variable, the output, and the dependent variable. Now, I mentioned the idea of a relation first because when you begin looking at the definition of a function is actually a special relation that we use in algebra and in other mathematics courses to model different phenomenon in our world. And it's a very important concept. It's actually one of the major concepts within college algebra. What makes the function a special relation is that for each valid input always determines exactly one output. Each valid input always determines exactly one output is the special characteristic that makes a relation a function. And pretty much anything can be a relation because we can relate any two things some way. But then if you go a step further, is it actually a function? Now, to emphasize that we're dealing with a function, we have a special notation. Here's the actual formal definition of a function from a mathematical perspective. A function is a relation in which no two ordered pairs have the same first component and different second components. And we'll look at some examples in a little while that will maybe help you make sense of more what that definition is saying. Basically, if you put it in good old everyday language, we're basically saying there's going to be no repeat of the X values, that every X value is paired with an individual Y value, and there's no repeat in the X values. Again, we use a special notation to emphasize that a function or that a relation is a function. And it looks this way, kind of right here at this second bullet point. We write it y equals f of x. And that's how you read it. Y equals f of x. Now, a lot of people want to think, well, oh, those parentheses mean to multiply. But remember, within mathematics, parentheses really are used to do several different things. They have different roles, and so you have to pay attention to the context. One, yes, we can use parentheses to indicate multiplication. For example, if I wanted to do 3 times 4, and I could put them in parentheses, and that would indicate for us to multiply them. They're also used for grouping. Okay, so if we had something like 3 plus 5 minus 2, okay, the parentheses would tell me it has the 5 minus 2 grouped together, and we would know to do that first. So you'd have 3 plus 3, which is ultimately 6. And the third thing that they're used for, they're basically just used as separation symbols. They're just trying to separate two different things, which is actually the scenario that we have here. So these particular parentheses are simply separating the letter F from the X. Now, what do the X and the F represent? The F here is actually just the name of the function. Now, we typically do use the letter F because function starts with an F, but it doesn't have to be an F. If you were representing, say, profit for a business, you might use the letter P for profit. If you were looking at revenue, you might use the letter R. So sometimes the name of the function, just like you all have different names, the name of the function can change. It's typically a lowercase letter, but it could also be, excuse me, an uppercase letter. Again, it's just how the name, how they are labeling that particular function. Then you have the parentheses, again, being used as separation symbols, and then you have, in this case, the letter X inside the parentheses, but that actually represents your input or the independent variable. And again, in most cases in algebra, we do prefer to use the letter X, but again, it doesn't always have to be an X. For example, if we were doing time, we might use the letter T. If you were doing, say, dollars, we might use the letter D. So it's just it's a fancy way, shorthand notation within algebra to emphasize that you're dealing with a function so that the reader doesn't have to actually go through the process of determining whether or not it is a function or not. So, and f of x represents the same thing as y. So in basic algebra, you're used to dealing with, say, ordered pairs in the form x, comma, y. When we begin thinking about functions, we think about them as x and f of x. It's the same thing. Y and f of x are interchangeable. All the things that you know you can do with equations that involve x and y, you can also do with functions that involve x and f of x. For example, it might be that you're asked to evaluate a function, and quite honestly, if you're asked to evaluate a function, it comes down to plug and chug. You got to substitute the number into the problem. So if we look at this particular equation, we have x squared, or function, x squared plus 3x minus 4. And then I want to evaluate f of 2. So they're asking me this 2 is my x value, which is my input. So I'm going to substitute 2 into the equation or the function wherever there is an x. Okay, so I would have 2 squared plus 3 times 2 minus 4. and then you do the math. You can use a calculator. You can do it in your head. 2 squared is 4, plus 3 times 2 is 6, minus 4. 4 plus 6 is 10, minus 4, which is ultimately 6. So we have, and a lot of times you'll see the answer written this way. F at 2 equals 6. If you wanted to write it as an ordered pair, you would have the ordered pair 2, with X is your 2, or your input, and your output is 6. So there's lots of different ways to express the answer, whether you express it as an ordered pair or just as an equation. All right, so then the next one, F at -3. Again, in this scenario, your X, which is your input, is -3. So we substitute -3 into the original function wherever there is an X. So I would have -3 squared plus 3 times -3 minus 4. And again, you can do the math. You can do it in your head or you can do it on your calculator. -3 squared is +9. +3 times -3 is -9 minus 4. 9 minus 9 is 0. Minus 4 gives us a result of -4. And again, if you want to write that as an ordered pair, you would have the ordered pair -3, -4. You can also evaluate it for a value such as A, okay? Instead of evaluating it for a number, you can do A. So in this case, my input is A. So wherever there's an X, I'm going to substitute A. So I'd have A squared plus 3A minus 4. Now, when I'm finished, there's really no simplifying I can do there. There's no like terms. That's simply the answer. F at A equals A squared plus 3A minus 4. Okay, a couple more. You could also be asked to use an expression instead of using a value or just a letter. There could be an expression like A plus H. So in this case, they want us to substitute A plus H. That's our input, and it goes in place of X. So we would have A plus H squared plus 3 times A plus H minus 4. Okay, now remember to square A plus H. Be careful. Here's a mistake a lot of students make. This is literally A plus H times A plus H. And you want to FOIL that out. So if we FOIL that out, we have A squared plus AH plus AH plus H squared. Then I also need to distribute the 3 through the parentheses. So I'd have plus 3A plus 3H, and then the minus 4 still tagged at the end. There are a couple of like terms there, so when I put all this together, I have A squared plus 2AH plus H squared plus 3A plus 3H minus 4. Now, this last formula, or this last question is kind of a special formula. I've got A's in there, but you could also do it with X's. This is an equation called the difference quotient. And I mention it here in this idea of evaluating a function because this is one of the things that you need later on as you progress through the upper level math. In fact, the difference quotient is one of the basic formulas that you use within calculus. And so it's important that you know how to evaluate a function so that you can apply the difference quotient. Now, basically it's a formula. They want us to take f of a plus h, which I've calculated just right above here. It's this expression up here. So I'm going to substitute that in. Okay, so I have a squared plus 2ah plus h squared plus 3a plus 3h minus 4. Then you have the minus sign, and then they want you to put in f of a. And f of a is back one slide back. I'm going to back up for just a minute so you can see it. F of a was this expression right here in purple. A squared plus 3a minus 4. So I'm going to substitute that in. So I have a squared well, let's see. A squared plus 3a minus 4, and then that whole expression, that whole thing is ultimately divided by h. Okay, so the first thing that I need to do is to combine like terms. Now be careful because you need to distribute this negative. Okay, so I have a squared. Get a different color here so you can see it better. Okay, you have a squared minus a squared, okay, which is going to give me no a squared. You have a squared minus a squared, those zero out. I also have, let's see, 3a minus 3a, so those zero out. I have minus 4 minus a minus 4, which is really plus 4, and those zero out. So then I'm left with 2ah plus h squared plus 3h, all divided by h. I then notice that all of the pieces have an h in them in the numerator. See, h, at least one h. So I'm going to factor out an h, and I'm left with 2a plus h plus 3 all over h in the denominator. Then, since I have an h in the numerator and an h in the denominator, I can divide those out. And I'm left with 2a plus h plus 3. Now, if we were in a calculus class, we would then spend some time thinking about what happens to this particular function or this particular equation as h gets larger and larger and larger and larger, or as h gets smaller and smaller and smaller and smaller. Okay, but again, it's just kind of a precursor to something, a skill that you need to learn in college algebra that you're going to use later on in calculus. Other things that you can do with functions, you can also be asked to express an equation in terms of a function. This particular one, the first example says express 2n plus 6p equals 12 as a function of p. So basically, in those fancy words, they're trying to ask you to solve that particular equation for p. So hopefully that's something you already know how to do. So if I'm going to try to solve this equation for p, I'm going to subtract 2n from either side to get the p by itself. So I have 6p equals negative 2n plus 12. Then I need to divide everything by 6 because I want only p, not 6p. So divide everything by 6. And when I do that, I have p equals negative 2/6, but that'll simplify to 1/3 n plus 2. So this equation written in terms of p, so we could actually now write this as f at n equals negative 1/3 n plus 2. Again, they're just using fancy language to ask you to solve the equation for a particular variable. Same thing with the second problem here, x minus 8y to the third equals 0, and they want you to write it in terms of y, which means you're trying to solve for y. So I would subtract x from either side. So I have negative 8x to the third equals negative x. Then I'm going to divide both sides by negative 8 so that I have y to the third equals x over 8. Negative over negative makes it positive. Then I need to undo the cube. To undo the cube, we take the cube root of both sides so that I have y equals the cube root of x over 8. Now we actually can simplify that radical because you don't leave fractions under the radical. Okay, so I would break this apart. I'd have the cube root of x in the numerator and the cube root of 8 in the denominator. And then I need to simplify the denominator if at all possible. So I have the cube root of x over 2 because 2 cubed is 8. So I can rewrite that expression as f of x equals the cube root of x divided by 2. You can also be asked basically to solve the function. If you're given a value for h of x, which is basically your y value, then you can actually solve the equation for x. So for example, in this first one, it says solve for h of x equals 3. So I would have 3 equals x squared plus 2x. And then I want to solve for x. So I'm going to subtract 3 from either side. So I have 0 equals x squared plus 2x minus 3. Since that has a squared term, my thought goes to quadratics and the fact that it probably will factor. So I need a pair of numbers that will multiply to 3 and subtract to 2. So that's 3 and 1 is plus 3 and minus 1. And then we know one of those pieces had to be 0. So either x plus 3 is 0 or x minus 1 is 0. And if I solve each respectively for x, I have x equals negative 3 or x equals positive 1. The second function is g of x equals the square root of x minus 4. And it wants us to solve when g of x equals 2. So I would have 2 equals the square root of x minus 4. Then I'm going to solve that for x, but to do that, I have to get rid of the square root, which means I need to square both sides. So 2 squared is 4 equals, just plain old x minus 4 because the square root and the square will cancel one another off. And then I solve that for x by adding 4 to either side. So I have x equals 8. Okay, now there are actually 5 different representations of functions, and so it's going to take me a little bit of time to go through those particular representation, so I'm going to stop the video and then create another one so it's not too terribly long for you.